In this first lecture on Chapter 10, I want to talk a little bit about the characteristics of gases and their properties that make it so that we can study them pretty easily compared to the solids and liquids. I also want to take a look at pressure. Pressure is one of the main variables that we look at when we study gases. There are a lot of different units that can be used to classify or measure pressure. So we'll take a look at some of those. I am breaking apart Chapter 10 into several lectures because there is a lot of information packed into this chapter, and I don't want to completely overwhelm you. So when we look at the characteristics of gases, what we notice is that gases will have different chemical properties, but very similar physical properties. Gases, no matter what type they are very similar in the way that they react to the environment around them. So the way that they react to pressure changes or temperature changes or volume changes. So even though their chemical properties are different, because they're made up of different elements, their physical properties are very similar, and that allows us to study them quite readily. When we look at the periodic table and all of the different elements, what we see is that most of them, of course, are solids. And we have two liquids, bromine and mercury. And then we have gases. 10 gases exist at room temperature. Of course, we have the noble gases, group 18, that consists of helium, neon, argon, krypton, and xenon. And you'll notice those are monoatomic. So a lot of times we've talked about how different elements, and in particular gases, exist in nature in diatomic form. However, the noble gases do not. Remember, they are pretty much inert or non-reactive. So the noble gases exist in nature as monoatomic gases. And then we have 5 diatomic gases: hydrogen, oxygen, nitrogen, fluorine, and chlorine. Now keep in mind that we have 7 diatoms that exist in nature, but bromine and iodine are not gases at room temperature. One characteristic that we can identify of gases is that they expand to fill the container they are in. Gases have no definite shape and no definite volume. So when we put gases into a container, they will expand. So the volume of the container is the same as the volume of the gas. If you have a 2-liter container, then you will have 2 liters of gas. If you have a 100-liter container, you will have 100 liters of gas, because the gas will expand to fill up the entire container. Gases are also highly compressible. When pressure is applied, volume readily decreases. So when we have a container that has, for instance, a piston in it, and pressure is applied, then volume is going to decrease. We can't do that with liquids or with solids. 2 or more gases are going to form a homogeneous mixture regardless of what the gases are. And an example of this is air. We know that air is made up of nitrogen, oxygen, argon, water vapor, carbon dioxide, all kinds of different gases. But we can't identify where the nitrogen is, where the oxygen is, where the carbon dioxide is, because they form a homogeneous mixture. The molecules completely move around to where we cannot identify where the oxygen is or where the carbon dioxide is, where the nitrogen is, and so on. We can't do that with solids. We can do that with some liquids, but not all. Remember when we looked at our lab on when we made emulsions? Remember we were mixing, oil and vinegar and trying to find something that would allow them to mix. Sometimes we can form homogeneous mixtures with liquids, but not always. However, with gases, this always happens. They are going to form a homogeneous mixture. These properties occur because gas molecules are far apart. So when you have a mixture of gases and they expand to fill the container so that their volume equals the volume of the container, they essentially behave as if they are alone, because gas molecules are relatively far apart from one another. If we consider that compared with solids and liquids, we know that for solids, the molecules are packed very tightly together. With liquids, there's a little room in between them. But with gases, they're very far apart. So they behave almost as if they were alone and that there weren't any other molecules with them. Pressure is one of the main ideas or main concepts that we study with gases. And you'll see when we get to the gas laws here in a little bit that pressure is going to play a key role. So pressure conveys the idea of a force. And we can see our equation here. Pressure is equal to force divided by area. Gases are going to exert a pressure on any surface that they contact. So when we have gases, for instance, in a balloon, if we blow up a balloon, gases are going to exert pressure. As those gas molecules are bouncing around, they're hitting the sides, the inside part of the balloon. But at the same time, the atmospheric gases, the air around us, are exerting pressure on the outside surface of the balloon. And in order to blow up a balloon, you have to put, more pressure into the balloon than what's on the atmosphere. So you have to kind of fight that atmospheric pressure. Now, the atmospheric pressure is the force exerted on anything by the atmosphere, and it's influenced by gravity. So we know that gravity is the force that basically keeps us here on Earth, that allows our feet to hit the ground. Well, that same force is applied to the atmosphere around us. So the gases in the atmosphere exert a pressure on us, on everything. So if we look at kind of deriving what this pressure is, we first have to consider force. So remember, pressure is force divided by area. So what is force? Force is mass times acceleration due to gravity. Okay. Now, acceleration due to gravity is a constant. It's 9.8 meters per second squared. So anything at sea level, anything on Earth, I don't want to say sea level, anything at the surface of the Earth has an acceleration due to gravity of 9.8 meters per second squared. So a column of air that is 1 meter squared, so that's its area, extending up through the atmosphere, so going all the way through the atmosphere, has a mass of 10,000 kilograms. So if we complete this equation, we get 1 times 10 to the 5 kilogram per meter over second squared, which is equal to a Newton. And Newton, named after Isaac Newton, is the SI unit of force. So a column of air that is 1 meter squared, so it has an area of 1 meter squared, has a force of 1 times 10 to the 5 newtons. So if we plug that in to our pressure equation and divide that by the area of our column, 1 meter squared, we get 1 times 10 to the 5 Newton per meter squared, which is equal to a Pascal, named after Blaise Pascal, who did a lot of studies with pressure. And Pascal is the SI unit for pressure. So 1 Pascal is equal to 1 Newton per meter squared. And that's the 1 times 10 to the 5 pascals is atmospheric pressure at sea level. Now, bar is a related pressure unit. You see there that 1 bar is equal to 10 to the 5 pascals, or 100 kilopascals. Now, when this idea was first coming around, people were very skeptical. And Torricelli, an Italian scientist, invented a barometer where he used mercury to help identify the pressure exerted by the atmosphere. And he did some experiments where he had a barometer at the base of a mountain and he took a barometer up to the top of the mountain and noticed that they were different, which they should be. As you increase in altitude, your pressure decreases. There's not as much atmosphere there to put the weight on you, or to put that force on you. So Pascal was on his side. Pascal understood what Torricelli was trying to do. And so at sea level, we have a column of mercury in a barometer that's 760 millimeters high. So that has become our standard for atmospheric pressure. And that's equal to 101.325 times 10 to the 5 pascals. So remember, Pascal is our SI unit for pressure. But we tend to use millimeters of mercury because that's the equipment that we use to actually physically measure the barometric pressure. Now, torr is equal to 1 torr is equal to 1 millimeter of mercury. So Torricelli got a unit named after him. Now, why it's not capitalized is kind of the funny thing here. You know, all of these others that we've talked about that have been named after someone have been capitalized, not torr. Okay, it is lowercase. So 760 millimeters of mercury, which is the barometric pressure at sea level, is referred to as 1 atmosphere of pressure. An atmosphere has become the unit that we use in the ideal gas equation, which we'll talk about in a little bit. So we have millimeters of mercury, torr, pascal, kilopascal, bar, atmosphere, psi, which is pounds per square inch. That's the one that we tend to use a lot in the United States. That's kind of the English system. We're familiar with pounds and we're familiar with inches. And that's also equal to 29.9 inches of mercury. If you watch the weather, they tend to give the barometric pressure in inches of mercury. Again, we're more familiar with inches than we are, millimeters or centimeters. So they tend to use inches of mercury. And we can convert between these as needed because we have these conversion factors that we can use. I'm going to stop here and then pick back up with Boyle's Law in the next lecture presentation.